Hi guys, I hope Part A made per unit a bit more clearer, not only how per unit works but why it works. And now in Part B we'll apply per unit to some real power systems engineering problems and demonstrate how per unit makes doing calculations associated with power system engineering a lot more simpler and less laborious. If you haven't watched Part A, I thoroughly recommend that you watch Part A before you watch this Part B. The link is in the description. It will give you a bit more of an insight into how and why per unit works, and it's good to have that grounding before we move on to show how per unit makes solving problems in power systems engineering more simple. Thank you. We're now going to run through a proper power systems per unit example. This will hopefully highlight why per unit makes solving power systems problems a lot more simple. To make things simpler, this is going to be a single phase example. And so the question we're going to try and answer is, what is the fault current at point M if a fault occurs at point F in the below system? And we'll quickly draw the system. So we're going to have a basic generator. It's going to be operating at nominal voltage, and the nominal voltage will be 22 kV. It's going to have an internal reactance of, and all resistances will be neglected, and also to make things simpler and quicker, all transformers will have an impedance of 0. But the generator will have an internal reactance of, let's say, 0.363 ohms. And then that will run to a transformer of 0 impedance. And that will step the voltage up. We'll call that transformer A. And that will step the voltage up to 275. 275 kV, and then we'll have an overhead line. We'll call that overhead line A, and that overhead line has an impedance of 0.121 ohms. And then we'll go to another transformer, again with no impedance. We'll call that transformer B, and that will set the voltage down to 132 kV. These are pretty standard transmission voltages for the UK network, and we'll call that overhead line B, and again we will put that at 0.121 ohms. And then we'll go down to, let's say, a final transformer, and that will step down the voltage even further to 33 kV, and we'll call it transformer C. And again there'll be a final overhead line to point F, where there is a fault in the system. And this is 33 kV. This is overhead line C, and we'll give this one a slightly different impedance. We'll give it 0.196 ohms. So, and we forgot to define point M, and we'll call that point there point M. So there is a fault in our system at point F, so current's going to flow from our generator through these transformers and overhead lines to point F, and obviously as it goes through here the current will go down as the voltage goes up thanks to the transformers, and then up as the voltage goes down, and then up even further as the voltage goes down even further to the fault at point F. And we want to know what is the current between transformer A and transformer B, just to the right of overhead line A at point M. So a pretty standard fault level problem for power systems engineering. And so we first need to define our system, which is with the relevant equations, and again this is all single phase, so you can forget about the square root of 3. So let's say we're going to use power equals V squared over Z, just a basic power equation. But in our case this doesn't define our whole system because there's a multitude of voltages. So we're also going to need some more equations, but they're just the basic transformer equations. So if we were to term that 22 kV voltage 1, voltage 2 will simply be voltage 1 equals the turns ratio at transformer A will give you voltage 2. And exactly the same, voltage 2 times by the turns ratio at transformer B will give you voltage number 3, and voltage number 3 times by the turns ratio at transformer C will give you voltage number 4. So there's our 4 voltages, 22, 275, 132 and 33 kV are all defined by these basic transformer equations, and in conjunction with this equation the whole system is defined. So, first things first, we need to work out all our bases. So, with this equation, there's 3 variables, so we can arbitrarily define 2. And traditionally, you define power arbitrarily, so we'll just say 50 megawatts is our power base. And then our voltage base is a little bit more complicated, so we have to pick where our voltage base is applying. Let's start our generator and say our voltage 1 base equals the nominal voltage, which is convenient as the generator is operating at nominal voltage, to be 22 kilovolts. Now we've defined those two, we could easily define our Z impedance, of Z base, but we'll define that a bit later. First, now we've defined voltage 1 base, we've already been given the turns ratio of the transformer, which is 22 over 275, and so we automatically can work out voltage 2, and then again we've been given the turns ratio of transformer B, so we can work out voltage 3 and so on. So let's quickly do that. Let's define all of our voltage bases if we are to obey these basic equations here. So we've arbitrarily defined voltage base 1, and voltage base 2 is very simple. It's just going to be the 22 kV. I was rearranging this, so voltage 2 is just voltage 1 divided by the turns ratio, so voltage 1 is 22 kV divided by the turns ratio, and the turns ratio of transformer A, which is between the 22 kV and the 275 kV, is 22 kV over 275 kV. Obviously, that just gives you 275 kV. So if we choose 22 kV as our base 1, we're forced to use our base 2 as voltage base 2 as 275 kV, which is very convenient. And therefore our voltage 3 base, again, is just our voltage 2, which is 275 kV, divided by 275 kV over 132 kV, because our turns ratio of transformer B, which is between 275 and 132 kV. And funnily enough, that gives us 132 kV. And our final voltage base
voltage 4 base equals our voltage 3 base, 132 kV, divided by the turns ratio, which is 132 kV divided by 33 kV, because we are concerned with transformer C, which is between the 132 and the 33 kV. And surprise, surprise, that gives us 33 kV. So we have all of our voltage bases and our power base. So next thing is to get all of these ohms values into the per unit system. So the resistance of the generator, the resistance of the 3 overhead lines, and we're neglecting the resistance of the transformers. So let's work out our Z1 base, which is going to be voltage 1 base squared over power base, which is just the usual power equation, P equals V squared over Z. Oh, in fact we wrote up here. So using that to find our impedance base for zone 1, or the 22 kV area, will simply be 22 kV squared divided by 50 megawatts, which comes to 9.68 ohms. So that's our voltage base. That's our impedance base for the first area, which is 22 kV. So then we can convert our impedance here into the per unit system, and that's simple enough. So our generator impedance is simply just going to be the ohmic value divided by the base to put into per unit. So that will be 0.363 divided by 9.68 ohms. And that's going to give us 0.0375 per unit. So we've got our first impedance in per unit for the generator. Now we need to go along and do the next 3 overhead lines. So overhead line A, B and C. And then we'll have all of our impedances in the per unit system. So to continue, the impedance base for the second area, which is in relation to the 275 kV area, is the voltage base squared divided by the power base, which is just power equals voltage squared over impedance just rearranged, which is 275 kV, which is our voltage base, squared divided by our power base, which is the same throughout the system, which is 50 megawatts, equals 1,512.5 ohms. So that's our impedance base for the second voltage area, which is the 275 part. And therefore our overhead line A's impedance is, in per unit, is simply its impedance in ohms, which is given to us, which is 0.121 ohms, divided by our base for that area, which is 1,512.5 ohms, which gives us 0.00008 per unit. So that's our impedance of overhead line A in per unit is 0.0008 per unit, and then our impedance base for the third area, which is where the voltage is 132, is the same again, it's just voltage squared divided by the power base, or the voltage base squared divided by the power base, equals 132 kV squared divided by 50 megawatts, which equals 348.48 ohms. And so that's the impedance base for the 132 kV area, and therefore our overhead line B's impedance is its impedance in ohms divided by the base impedance for that voltage area, which is 132, so that's 348.48 ohms, which comes to 0.0003472 per unit. And then our impedance base for the 33 kV area, or 33 kV base area, is the voltage base squared divided by the power base, which is the same throughout. So that's 33 kV squared divided by 50 megawatts, which equals 21.78 ohms, and that is the base impedance for the 33 kV zone of the system. And therefore overhead line C, impedance in per unit is simply its impedance in ohms, which is 0.196, divided by the impedance for that zone, the impedance base for that zone, which is 21.78 ohms, and that comes to 0.008999 per unit. And if you're actually doing this in a three-phase example, the square root would come in relation to the power, but where this is just a single-phase example, to make things simpler and easier, there's no square root of 3 in any of these calculations. It can basically be forgotten about. So let's write our old system, but in the per unit, and it's a lot more simple. So it's our generator, then our generator's impedance, which we've calculated in per unit as 0.0375 per unit. Let me come along, and our overhead line A impedance is 0.00008 per unit, and that takes us to point M, where we're planning to measure the fault current, or we're trying to calculate the fault current at. And as you can see, now we put things in per unit, and the turns ratio of the transformers have been taken account in the bases of this per unit system. We can basically neglect the transformers. You can see we haven't written the first transformer, and we're not going to write the second either. They can all be neglected because the turns ratio has been factored into these per unit values thanks to the bases being related by the turns ratio of the transformers. And this is very important because this is what's going to make the calculations, the power systems calculations, a lot more simple. This fact that we can neglect these transformers once we've taken account of their turns ratio in the bases and defining all the bases. So let's continue. Then there's overhead line B, which is 0.0003472 per unit. And then we finally go to overhead line C, which is 0.008999 per unit. And then we have our fault at the end, at point F. So we can neglect all the transformers now, as we've taken account of the turns ratio in the bases of these per unit values. And it's very simple to calculate the total impedance. Now that we can neglect transformers, it's simply just the impedance of the generator plus the impedance of overhead line A plus the impedance of overhead line B plus the impedance of overhead line C. Whereas if we're going to do this in the real values, we'd obviously have to reflect these impedances through the transformers by the square of the turns ratio, which is very laborious, and then we would have to work out the step up and step down of all the voltages and currents. And this is what makes per unit so useful in power systems engineering. If we take account of the turns ratio of the transformers in the bases, then we can neglect them from that point. And there's obviously hundreds and hundreds of transformers typically in a transmission network or a distribution network, and therefore all this reflecting through the transformers by the square of the turns ratio or the turns ratio can then be neglected, making calculations so much simpler. And that's why the per unit system is used in power systems engineering, because it saves on a lot of laborious calculations. All these laborious calculations of converting endlessly through the transformers now can just be completely forgotten about as long as we do our calculations in the per unit system. And then all we have to do once we've completed our calculations is convert these per unit values into real values. One little simple basic step. So let's continue. So our total impedance in per unit is very simple. It's just all these three plus together. So it's the generator impedance plus overhead line A impedance plus overhead line B impedance plus overhead line C impedance, which if you add them all up, that value plus that value plus that value plus that value, the total impedance comes to 0.04692630395, and that's the total impedance in per unit. Now, as we said right at the beginning, the voltage of the generator is at nominal voltage, which was 22 kV. So 22 kV divided by the base of 22 kV is simply going to be 1, so the generator is at 1 per unit. And if we just use the basic voltage is current times my impedance, our fault current in per unit is 1 over our total impedance, which our total impedance was 0.0469263, etc. And 1 over that comes to 21.31000986 per unit. And that's the fault current in per unit through the entire system. Because as we were saying earlier, as the turns ratios have been taken account in the bases, this is actually the fault current through the entire system in per unit. We don't have to reflect by the turns ratio, and we don't have to reflect the fault current by the turns ratio to get the appropriate fault level at each and every point, because this value in per unit is the fault level throughout the whole system. And then at point M, which is the point we want to take the measurement of the fault current at, the voltage base is 275 kV, and therefore our current base, if we were just to use power equals current times by voltage and rearrange it, would be our power base divided by our voltage base, which is 50 megawatts divided by 275 kV, which comes to 181, 81, 81, 81, etc. So that's our current base at the 275 kV voltage, which is where our measurement point M is. Therefore, our fault level at point M in real values is simply our per unit value of 21.31000986, which is the per unit value of the fault current, times by our base at that relevant point at M, our current base at that relevant point M, which is 181.818181, which equals 3,874.547 amps. And that is our fault current given a fault at point F, measured at point M at the 275 kV. And that is how per unit makes solving power systems engineering problems with transformers in simpler than if you were to calculate this value by reflecting through all the transformers. But if you do calculate this value with just the raw values reflecting through all the transformers, you would come to the same value, and I asked you to check it. I've checked it, it is the same value. So that should show you how per unit makes calculations more simple and how you come to exactly the same value as you otherwise would if you use the real values. So thank you very much for watching, and I hope you learned something. Thank you.